Have you ever dropped a ball from your hand and watched it fall? At first it's still, and then suddenly it speeds up as it goes down. Why does this happen? And what happens to its energy? Hello everyone. In this session, we'll explore what really happens to a falling object, not just from a motion perspective, but from an energy point of view. Let's begin by understanding a key idea. When an object falls freely under gravity, it only has one force acting on it: weight, or gravitational pull. At the beginning of its fall, the object has potential energy because it's at a height. Its kinetic energy, on the other hand, is zero because it isn't moving yet. As it begins to fall, its speed increases, and kinetic energy builds up. But interestingly, potential energy decreases at the same time. This transformation is our gateway into something deeper. The total energy of the system doesn't vanish, it just changes form. Let's find out if this total mechanical energy remains constant. To get scientific, let's write down the formulas for both types of energy. Potential energy is given by U equals m into g into h, where m is the mass in kilograms, g is the acceleration due to gravity, and h is the height from the ground. Kinetic energy is given by k equals 1 by 2 into m into v squared, where v is the speed at that instant. Now, as the body falls, it loses height, so h reduces, and so does the potential energy. But speed increases, which means v increases. So kinetic energy goes up. The beauty is this: we'll soon see that k plus u remains constant throughout the fall, and that's what we're going to verify mathematically. To prove this, we need to relate velocity and height, so we use a classic kinematic equation from motion under gravity. It says v squared equals u squared plus 2gh. Now, since the object is released from rest, its initial velocity u is 0, so the equation simplifies to v squared equals 2gh. This links how fast the object is falling to how far it has fallen, and that's exactly what we need to compare kinetic energy and potential energy. This graph clearly shows that as potential energy goes down, kinetic energy rises, but their sum remains unchanged, demonstrating the conservation of mechanical energy. Now let's plug this velocity equation into the formula for kinetic energy. We already have k equals 1 by 2 into m into v squared. Substituting v squared equals 2gh, we get k equals 1 by 2 into m into open bracket 2gh, close bracket. Simplify that and you get k equals m into g into h. That means the kinetic energy gained by the falling object is exactly equal to the potential energy it has lost. It proves that the potential energy at a point is directly proportional to the height, and when the object falls, that same energy becomes kinetic energy, following the equation k equals m into g into h. Let's now verify the conservation of mechanical energy in a falling body. At any point during the fall, total mechanical energy is the sum of kinetic and potential energy, expressed as k plus u equals m multiplied by g multiplied by h. This total value stays exactly the same, whether the object is at the top, halfway down, or just about to hit the ground. Even though kinetic energy increases as the object falls and potential energy decreases, their combined total does not change. This unchanging total is what we call the conservation of mechanical energy. And remember, this principle only holds when air resistance is absent. If there's no energy lost to the surroundings, the system stays perfectly conserved. Let's apply all this to an example. Imagine a body of mass 2 kilograms falling from a height of 5 meters. At the top, U equals 2 into 10 into 5, which is 100 joules. K equals 0, so total energy is 100 joules. Midway, at 2.5 meters, U equals 2 into 10 into 2.5, which is 50 joules. K equals 100 minus 50, so 50 joules. Again, total energy is 100 joules. Just before hitting the ground, U equals 0, K equals 100 joules. Still, total energy remains 100 joules. No matter where the body is, top, middle, or bottom, total mechanical energy stays the same. Let's wrap up with a quick summary. Theoretical analysis confirms that during freefall, potential energy is fully converted into kinetic energy by the time the object reaches the ground. At every stage of the fall, whether halfway or just before impact, the sum of kinetic and potential energy equals the original energy the object had at the top. This means that the total mechanical energy remains constant, proving the law of conservation of energy. This principle isn't just theoretical, it's used in engineering, skydiving, roller coaster design, and even in understanding planetary motion. Grasping this idea helps us value how energy transforms in nature and how we can use it more efficiently in the real world.